So today I'm going to try to implement find package, which is a function on the cmake uh, language. I think is its own language, and I'm probably not gonna be able to do it because I've been trying already and is a pain in the ass to be honest. So I'm probably just gonna read the documentation and then try different stuff here. Yeah, so the main thing that I tried is to put. So as far as I understand now, I think there's two different modules, two different ways you can do it. One way is you can put this config here, and then it's gonna find for a file that has the name of the project and config right next to it, and the .cmake extension, I think. And if it doesn't find that, then it throws an error. And the other way is just a default way, I think, which is it searches for another type of file. And this function is to try to, not try to, but to download external modules into your project, as far as I understand now. So the other thing that I tried is this add subdirectory here. So what I'm trying to do is pretty much download or use the external module that is called JSON that allows you to read JSON files or to convert code encode and decode JSON files. It's JSON here. But the issue is that and I was using make files before, but the make files are very confusing. Like the more stuff that I put, I didn't like that much because I have to write the like in three different places and it's like starts getting confusing. And then I thought that cmake might be better because it is also cross-platform. So I think that cmake is probably the best solution. Like it's the most robust way to go about it. But so far I haven't. It's a lot more difficult than Python and JavaScript, and I don't like it very much. But I think the reason why it's like that is because it gives you more flexibility. So it's like harder to do, but it's more powerful. And yeah, I've heard a lot of people complain about this as well. So I was expecting to be hard, but it's still a pain in the ass to try to figure out. And then I tried to watch a bunch of videos. I watched a bunch of videos and I tried to implement, but the mistake that I'm getting here is that I'm using this config, which is supposed to find the config file. So the first thing that I did was to download the JSON library here. And then I followed the documentation and I used the cmake inside of this file here to build the project. So they recommend you to create a build directory and then you move to the build directory and then you run cmake from the project and then it builds all the files that the project needs. I think it builds the executables and these libraries here, I think. And then it also builds these files here. And I think these are the files that are supposed to be used on the other project to find this one. So this is the challenging thing is that the documentation of the JSON, they don't explain how to, like what you should do to, and I think that it doesn't make a lot of sense for them to explain because it's more of a general thing. But how you should go about incorporating the library into another project. And it's kind of hard because I think there isn't any standard. So it's the thing that I just talked about where you have more flexibility, but then it's harder to figure it out because then you can do pretty much anything you want. But I'm struggling to think about what is the best way to format or to put the files, like structure the project here. Because not because I don't know how it's gonna grow, but it's just difficult to know like what is usually the way that people do it. And I've seen some stuff and it seems like they recommend you to create an include folder and then put this stuff on include folder, but then some people use the build folder, and I was using the build folder because this project here comes from another course. So right now I decided to just go with the way that it is here and put the cmake and inside of the build folder that I have here, and then put the external library inside of the build folder as well. And now what I'm trying to do is just to see how can I incorporate this library here into the cmake that I have for the main one, so that I don't have to think about this later. And I was able to like kind of solve, but the issue is that I can't import in the way that they recommend you to import, which is just using the name of the library here. So I assume that I'm probably doing some stuff wrong. I think that I can, like I can pass the relative path to this file here, and then I found a way to make it work, but I think it's not probably the best way to go about it. So what I have to do is just understand more. And there's a lot of stuff. The language is not that hard, I think, but the biggest issue is that like I don't know where the source code is, and I don't know what it's doing like under the hood. But at the same time, I think it's good to learn this because I'm not 100% sure, but I think that probably the other package managers come from the same logic that this one have. But because this one is more at lower level, you have to manually do this stuff yourself. And so far, I'm already seeing these kinds of things here that I think the other package manager do. And cmake doesn't do, which one of them is to download external libraries. So I think that the way that it works is is like code that builds a server and a client on the other package managers. And then every time you run a command like yarn or pip install, for example, what it's actually doing is just calling a bunch of code that is gonna set up the server and client dynamic to fetch the code from somewhere in the internet, and then after it does that, it creates the logic on the shell to create the files and put them on a specific place. And I think that it's easier on JavaScript and Python because of that, because you have the standard. So there's always the trade-off, and it makes sense that like the Python and JavaScript make a lot of more sense to me than this way here. So, but it's also at the same time like part of the whole structure of things, because it's going to be a funnel. So the lower level you go, like there's a trade-off, and I think that there isn't any right or wrong answer. It's always going to depend on the environment. So yeah, but so the way that you do it is you just go over the build folder, and then you run a command to build the project first, or to like initialize the cmake files, I think. Yeah, which is this one. And also for the way that I was doing, I was having a problem because if you don't pass this argument here, the flag variable, which is this G, at the capital G flag variable, and then you specify this thing here, it just is gonna use the default compiler to build the files. And the problem with that is that when I was running that, when I would try to build the project, it was using the MS build compiler, I think, which is different than the one that I was using before, which is the GCC compiler. And because of that, I was getting a bunch of errors on the code. So I think the default compiler is whatever compiler is going to be like the default on your operational system, but I'm not 100% sure. And when you're using Windows, it's most likely to be the one from Visual Studio, which is MS build, which is different from GCC, which I think is the default on Linux probably. So if you want the cmake should be built with the GCC compiler, then you have to install this thing here, which I already had installed, but if you don't, you have to install, then you have to put that on your path, which these environment variables is just a way that the operational system becomes aware of the code. So whatever you put in the path here is gonna be like a folder that contains executables, and then after you put that, you can just type the name of the executables on the command line, and the operational system is going to understand what it is. So you install that and put it on the path. After you put it on the path, then if you tell cmake to use this, then when you're building the project, it's going to use the GCC compiler instead of using the MS build one. Hey, no new. cmake is a cross-platform cross-platform make. Like, do you know Python or JavaScript? The easiest way to explain is just like the npm or yarn for C. or the pip for C. So it's like a, but it's not really a package manager because you do have other package managers on C, for C or C++. It's more a thing that allows you to build the logic for what would be a package manager in the way that I understand right now. So like a make file allows you to run a bunch of commands on the shell without having to run them manually. So it's just a file that has its own language. And then once you call the make command, which is the thing that I was just explaining now, that is an executable that you put on the path of the system. And then it's going to call that executable, which is going to be the make and the make command. So when you run make, it's going to search for the make file on the directory. And then the make file is going to have its own language. And it's going to run whatever commands you have here, which is just shell commands, I think. So in this file, you put labels, and then the labels described what is going to be run. And then here are the commands that it runs, and it runs everything for you. So you don't have to type all these commands separately. You just run make and it runs whatever it is here. Or you can pass a flag, which is going to be the label. So if you run make clean, it's going to run the commands you have here. And GCC is the compiler for C. So, and the cmake is the thing that creates make files for you. So, because different operational systems have different things, or like it is a different way that the machine code becomes a higher level programming language, which depends on something called the instruction set architecture, which is the standards, which I just learned recently, but is the standards that they created for making some machine code have meaning on the assembly language. So each hardware is going to have its own instruction set architecture, which is going to convert to a different assembly language. And then the higher level languages eventually are boiled down to the assembly level. So the issue is that if you're using Linux, for example, to build a project with C, then if you move to Windows, it's not going to be the same. So you would theoretically have to create two different make files, I think, to run on the two different systems. But if you use cmake, then it creates the make file that works on both for you, as far as I understand right now. So, but I don't know like much about it. I'm just learning now. So yeah, this is what I have so far. So after you build here, then you run this. After you do the initial setup, which setups the make files, and I think it just setups the initial cmake files. Then after you do that, then you call this build here, and then you pass whatever path you have, whatever the path the cmake files are. So in this case, it's on the build directory, so I'm passing the dot here. And the other command, you have to specify the source, which is where the entry point of your project is going to be. So you pass the two dots here because I'm on the build directory. So I want to go one directory up because that's the like root point of the project. And yeah, so you pass the source and then you build the initial. And then after that, you run this build command. And that's the command that does the compilation, I think. So this is probably the command that runs everything that you have on the cmake list file and sets everything up, compiles everything, and does whatever you put here. So yeah, but now I'm getting the error because I'm trying to do this and it's not finding the files here. And then I did some stuff to make it find the files, and I got another error. And I think the reason why I got the other error is because probably cmake changed in the way that it finds the files. So before you were supposed to have these files here, but now you're supposed to have target JSON and target file. So it's just pretty much just complaining that I don't have another file that I'm supposed to have. And I think it's just because of the versions of the libraries. So this is an older library, but I'm using a new cmake version. And then it looks for a different kind of library and doesn't find it. So I have to figure out what I have to do to make it work. So there's a bunch of things that I'm thinking about, like a bunch of different alternatives that I can go about it. But the challenging part is that I don't know which one is the best, like in the structural sense of the whole project itself, because I can find a hacky way to make it work, I think, but then like, is that the best way? And I'm not really sure if that matters or not. So I'm working on a project that is going to convert the code into a visualization to make it easier to understand how complex projects work, because that's the main challenge I had when learning by myself. So if you go into a GitHub repository, there's going to be a bunch of files and folders, and it's going to be very complex because that's how code scales. So the challenge is going to be how do you understand the whole design of the thing and how everything is connected. And the issue is if you go manually into each function and each file, then it's like very inefficient, because you're trying to, like, you have to go back and forth between files all the time, and you have to keep track mentally on your mind of what variables do what and how they're going to change over time. So I think that is, but I'm not 100% sure if that's the case or not. But as far as I think right now, is you will probably be like more efficient if I'm able to look into the code as a graph, because then it allows me to see everything at the same time. But I'm not 100% sure if that's the case or not. It's just my intuition. So what I'm trying to do is just use use the C compiler here to create a graph visualization out of the structure of code, so I can look into a graph. And then based on the graph, I'm able to, like, hopefully I'll be able to understand more the projects, and then I can use the graphs that I build to study other stuff, and then I like generate the feedback loop system of recursive self-improvement. That's the goal. So here I got this compiler from a course, and I'm trying to modify the source code so it does what I want. And then the plan is to use that on the CPython interpreter to understand how the Python interpreter works. And then once I understand how the Python interpreter works, I can modify or change the Python interpreter as well to break down Python code as well. And then I'm going to do the same thing for JavaScript. But I don't have any experience with C, so I'm trying to understand like what is the best way to structure everything. So the challenge here as well is that I don't like I didn't like the documentation very much, because like it doesn't explain. I think they assume that, or probably I should know some stuff that I don't know, or they assuming that I should know, because it's kind of vague as far as I feel like. I'm gonna go back and then just read the things one by one, I think, with the text to speech. But like the commands are simple, but then that's the issue. Like when something happens, and I, one thing that I can do, I think, is just like this project has this source here, which has all these files, and I think that these are all the files that are gonna create the code. And then it says it only has this header file here. So the problem is if I import this on a relative way, which was the way that I was trying to do, that it works, but then I think that the definitions of the functions don't work, because you have to compile all the C files into object files. So it finds the definition. So even though the import starts working, the definition doesn't exist, because it's just finding the header file, but it doesn't find the object files that have the function. So I have to figure out a way to compile everything. And then obviously what I can do is just, I can either use the make file and then put all the commands in the same way that the other make file was working, and then find the path that I'm going to put all the object files from the JSON thing, and then use that to build. But then I think that's not very good. So the other thing I'm thinking about doing that I can do is just put the files here. So the way that it works is that this command here sets whatever variable you put here to be equal to whatever arguments you put after the name here. So this creates a source files variable that's going to contain all these files. And then you have this add executable, which everyone recommends, as far as the thing, to put whatever code you want to build first. So it's kind of different than the cmake one, because on cmake you put the name of the file, and then you put the output, the flag variable output to select where the object file is going to be. But I think with here is different. I think you have to build the executables for all the files, and you don't build object files, as far as I know, but I could be wrong, obviously. But then you put the way that you use the flag variables is the same way you use the flag variables on JavaScript, which is just putting $sign, then the curly braces, and then the variable name. And then the language itself has some environment variables that you can use, and project name is one of them, which is going to be just the name you put here, just specify. So you have to do this in the beginning, which is put the required version here, which is the minimum required version, and then you put the project, which is going to be the project name. And the rest is kind of arbitrary, but this one is one that you probably are going to use all the time, which is just to select the entry point of the application, I think. So you put the project name and the name of the main file, and then here is just going to replace this stuff with all these other files here, which are all the source files for your project. And then this creates the executable, I think. So, and it's going to create the executable, the main executable on the file that the build command is running from, which in this case is going to be the build folder. So you just create an executable at the end with the name. I think I deleted from here, but it creates with the name of the project, not the name of the file. So if you want, the way that I was doing before with the make file is going to create the main.x, which is going to be the main thing. But this one creates the ccompiler.x, which is the name of the project. And it's going to be the main executable. And then this stuff here, I don't understand really well. But I think that this is the same as the I flag thing on the make file, which just allows you to specify the path where cmake is going to look for all the header files. So this one I got from ChatGPT, and I think what it does here, like I know what it does based on just the conceptual level of the instruction, but I don't understand really well the nuances of it. But what it does is just it specifies the path should be this environment variable, which is the entry point, the root point of the project. So cmake current source dir, which is the directory of the file of the cmake list text file. So this maybe this is wrong actually, now that I think about it, because maybe oh no, I think it's right because I put the cmake list file on here. Yeah, so it's kind of confusing because you have you have to put the cmake list text file on the root of the project, but then you build the stuff inside of whatever directory you want, but most people recommend to use the build directory. And I think some people use the alt directory. Can you increase video quality? No, there's nothing I can do about that. Sorry. Just internet, the upload of the internet. What do you want to know about header files? And I don't know that much, so like take everything that I say with a grain of salt because I'm still learning as well. See, pragma is a command that allows you to specify to run the header file only once. So you can use pragma or you can use if and if def, this command here, and then you end the if in the end of the file. So what this command does is allows you to specify only run this header file once. And the reason why this is useful is because if you're downloading several external libraries, there might be the case where like you import it, for example, you import this compiler age library on other header files and other C files. And then what happens is that you would be importing the same file several different times because other programs use the same library. So in order to avoid that, you specify this thing here. And then instead of importing the library, it's just gonna look for the definition, as far as I understand. So
Introduction, Pilpro. cmake is a tool to manage building of source code. Originally, cmake was designed as a generator for various dialects of makefile. Today, cmake generates modern build systems such as Ninja as well as project files for IDEs such as Visual Studio and Xcode. cmake is widely used for the C and C++ languages, but it may be used to build source code of other languages too. People encountering cmake for the first time may have different initial goals. To learn how to build a source code package downloaded from the internet, start with the user interaction guide. This will detail the steps needed to run the cmake 1 or cmake GUI 1 executable and how to choose a generator, and how to complete the build. The using dependencies guide is aimed at developers wishing to get started using a third-party library. For developers starting a project using cmake, the cmake tutorial is a suitable starting point. The cmake build system 7 manual is aimed at developers expanding their knowledge of maintaining a build system and becoming familiar with the build targets that can be represented in cmake. The cmake packages 7 manual explains how to create packages which can easily be consumed by third-party cmake-based build systems. Index and search GoPro. Quick search. Copyright 2000 to 2023 Kitware Incorporated.
So maybe I should. I think. I think it was complaining about. I don't understand this very well, but I think that like this is a standard, but it's not. I'm not 100% sure about this, but like the way that I was doing before, that it was kind of working. I think that this name here, like, is name of the file, name of the project, like name of the module, then underscore and dir. And I think that this is a standard that they create on cmake to find for this config files here. So if you put this name here and use set, it allows you to set the variable to whatever path you want. And I think that's the way that I was trying to do it before, which is probably not the best way, and that's the thing. But it was working, but I was getting another error, so maybe I'll try to do that now. And I think I was just passing this thing here, and then I was passing the path from where I could find these files here, which is on the build of the other project. And then what this does, I think, is sets this variable to be on this path, and then it finds these files here. But then the issue is that it gives another error that I don't understand really well. I mean, I think it's because they changed the way that it works. So now it searches for another file. Not really sure. Yeah, now it's not working. Or maybe I was doing something else. I don't remember really well. Oh, this is the thing as well, is that I found some videos as well that they recommend, or the way that they say to solve this is that you should run the thing with a flag variable that specifies this path here, I think, this prefix path, and I think that this is a way to solve it. So you run, instead of running the command like this, you pass this flag variable, and then you specify this path here, and then based on that, it's gonna find the file. But like the problem with that is that I don't like that solution, because then I have to remember the command each time that I'm gonna run. It's not very good. So like I think that there should be a way that I set something here or I specify something, and then it just allows me to find the thing. And the other thing is that if you use this add subdirectory here and I don't use the other ones, then I think it just, in the initial phase, let's say, it builds everything. So like one way you can do is just follow the documentation and then just build the cmake from this project here. So you create the build folder, and then you run the same commands I'm running now to run the actual project, but for the library itself or for the module itself. And then it builds all the cmake files. But another way is just to put this add subdirectory here. And then when you run the cmake for one project, it's just gonna run the cmake for the other one. So it's like a running for the sub directory. Very similar way that it works with Python, I think, with pip, where first you install the project, but then like on pip and yarn, you install the project first and then it does everything for you. Here you have to manually download. If you're not using a package manager, you manually download and then you run the command and then installs everything. So, and you have to specify here and then installs. But it's not related to building everything. So to finding the file. So what I have to do is just to clarify my mind, I think. I have to think about different ways that I can, like different solutions and which one is the best path to go. And the question that I have is whether or not I should compromise if I don't find, because based on the documentation that I've seen so far is not gonna have like, it's not gonna be very good to understand what is actually happening under the hood when you run the commands, and that's what I want to clarify, I think. So I want to know how is the code trying to build this stuff, so I can understand better how it works. But if I can't do that, then the compromise I think would be to just get the files on the source and then just use these files instead, and then just add the files here to this project. So, but another thing I have to clarify is the header files on here. I think the main thing is like the difference between external. So when you're importing an external thing, you use this symbol here, the arrow, whatever you say that, however you say that. And when you're importing a local header file, you use the string thing here. So I think that this is what I have to clarify more. But it's kind of hard to think about a good way to search because there's also not a lot of content. So what I want to understand is how does C looks for the files when it is an external package. So here when I'm using standard lib, what is happening under the hood to find the file? That's what I want to know. So like also the confusing thing is the object files and the executable files, because cmake builds the executables, and when you're using the make file directly, it builds the object files. And I think that on the object files, you're going to have the definitions for the functions, and the executable is going to look for the declaration on the header file, and then based on the declaration, it finds the definition on the object file. But with cmake, is building the executables and it's not building the object files. So what is the difference when it's linking everything? What's happening? And how is it finding the header files as well? And that's what I have to clarify. Because here there isn't any header files. So I think the only thing that makes sense is that based on the code here on the C files, it builds the linking process already just based on the C files, because the C files are going to contain the path for the header files. So finding the header files is more from the C code itself, like the C language itself, and building the everything. But that doesn't make sense because it has to be like both at the same time, I think. Like cmake has to be related, I think, in some way to creating the link between the headers and the code. The declaration of the function, the linking of the function with the declaration of the definition. And the reason why I want to understand this is because even though if I solve here, like maybe I find a way to solve it and then it works, like it compiles everything, but then I still can't use the declaration of the file because it's looking for other path. And then like I'm not really sure if it would be good or not to, let's say, to put the relative path here, which I've seen some people do, I think, but I'm not really sure if it's good or not. Where like I would put like the relative path to find the file here instead of just putting JSON. The documentation recommends you to put just JSON. So I assume that based on the cmake process, I should specify somehow like how to find the file. And I think that probably this is the purpose of the find package. But this is the challenge here because I think that the documentation doesn't explain very well like this process of finding the file. So I'm not really sure. Yeah, I guess this is the main point of confusion I have so far because it's not very clear what is happening under the hood with all these commands and how is it finding each thing when you specify here. So I guess what I have to clarify is first the commands, like the commands that I'm not sure about, and then maybe I look into the module thing after. I'll be right back, but I'm probably gonna read the documentation now and try to understand how the source code works. Not the source code, but how do they? Which that's the thing. Like I'm struggling to find a way to clarify how should I build questions to clarify the way that I'm thinking now, because I think I already understand roughly how the commands work, but it doesn't help in trying to solve the thing. But maybe the first thing that I should do is just try to make it work with the thing here like I was making it work before. Because I was putting some command here and I think that it was fine in the config files. And then instead of this error, I was getting another error. So, but I really don't wanna, I wanna avoid at all costs having to do some special command that is gonna specify a path based on the command line, because then I have to remember the command each time that I'm gonna run. And I think that's not very good. Like, it's much better if I can just put all the code on the cmake list file, and then I can forget about that, and then just focus on building the actual stuff later. So that's what I want to achieve. I'm gonna leave this one here because I think it doesn't change anything. Oh, I think I have to put build first. I forgot the build. Let's build, then JSON, then build, then cmake. Because this is inside of build, then is inside of JSON, then inside of build, inside cmake. So maybe this one will change the message. Yeah, now it gives me the other one, I think. So let me run with these other commands. Oh, I'm gonna try to put it here first, then if it doesn't work, I'll put it after the build thing. Yeah, so, but you can see here now that it complains about this other file here, JSON targets. So it says that, like, from everything that I've seen, that if you put the config command or argument here, it's gonna look for the source, for the path that has the file that has the name of the project and then config. like this here. So like when I don't put this stuff here, it doesn't find the file, so it complains that it didn't find that file. But then after I put this stuff here, then I think it finds the file, but now it complains that you don't have the JSON targets, which I don't understand why, because I haven't seen anywhere that you're supposed to have this thing here. And obviously it's not my code, it's the code from the library and the cmake from the library. So the only conclusion that it makes sense to me is that the library was built before they made some change on the cmake, and by the time the library was built, it wasn't necessary for this file here. So the version of cmake that they were using and that I used to build the project here doesn't create, or the logic that they created doesn't create this JSON targets file. So I have to think about a way that I can ask questions that are going to allow me to clarify what's going on. I think it has to be after. Whatever. I'll be right back.
Step 3. Adding usage requirements for a library pilpro. Exercise 1. Adding usage requirements for a library pilpro. Usage requirements of a target parameters allow for far better control over a library or executables link and include line while also giving more control over the transitive property of targets inside cmake. The primary commands that leverage usage requirements are target underscore compile underscore definitions, target underscore compile underscore options, target underscore include underscore directories, target underscore link underscore directories, target underscore link underscore options, target underscore precompile underscore headers, target underscore sources. Goal pilpro. Add usage requirements for a library. Helpful materials pilpro. Make underscore current underscore source underscore dear. Files to edit pilpro. Math function / make list.txt. Make list.txt. Getting started pilpro. In this exercise, we will refactor our code from adding a library to use the modern cmake approach. We will let our library define its own usage requirements so they are passed
And something I don't understand really well is when I should use these commands here. So I think that the include is probably the stuff that I was talking about, where it's just the I flag variable. So I think if I put this one here, it's already enough because it's gonna look for all the files that are below the level that I put here, which is the top of the project. So it's just gonna look for all the header files that exist inside of the project itself, and I don't need to specify. But at the same time, I don't know like why someone would do something different, and it's probably because there might be a benefit to specifying just specific directories, but yeah, I don't. I'm just gonna read the thing there, but I'm not really gonna spend a bunch of time, I think.
Transitively to other targets as necessary. In this case, math functions will specify any needed include directories itself. Then, the consuming target tutorial simply needs to link to math functions and not worry about any additional include directories. The starting source code is provided in the step 3 directory. In this exercise, complete Toto 1 through Toto 3. First, add a call to target underscore include underscore directories in math function slash cmake lists. Remember that cmake underscore current underscore source underscore dir is the path to the source directory currently being processed. Then, update and simplify the call to target underscore include underscore directories in the top level cmake list.txt. Build and run topro. Make a new directory called step 3 underscore build. Run the cmake executable or the cmake GUI to configure the project and then build it with your chosen build tool or by using cmake build. From the build directory, here's a refresher of what it looks like from the command line. With your step 3 underscore build cd step 3 underscore build cmake slash step 3 cmake build. Next, use the newly built tutorial and verify that it is working as expected. Solution copro. Let's update the code from the previous step to use the modern cmake approach of usage requirements. We want to state that anybody linking to math functions needs to include the current source directory, while math functions itself doesn't. This can be expressed with an interface usage requirement. Remember, interface means things that consumers require but the producer doesn't. At the end of math function slash cmake list.txt, use target underscore include underscore directories with the interface keyword as follows. Toto 1. Click to show slash hide answer Toto 1. Math function slash cmake list.txt pilpro target underscore include underscore directories math functions interface $cmake underscore current underscore source underscore dir. Now that we've specified usage requirements for math functions, we can safely remove our uses of the extra underscore includes variable from the top level. Toto 1. Click to show slash hide Toto 2. Click to show Toto 3. Click to show slash hide answer Toto 3. Cmake list.txt pilpro. Click to show slash hide the resulting code remaining code after removing extra underscore includes pilpro hash add the executable add underscore executable tutorial.cxx target underscore link underscore libraries tutorial public math functions tutorial underscore compiler underscore flags. We want to state that anybody linking to math functions needs to include the current source directory, while math functions itself doesn't. This can be expressed with an interface usage requirement. Remember, interface means things that consumers require but the producer doesn't. At the end of math function slash cmake list.txt.
Yeah, this is kind of hard to understand. So let me see. Anybody linking to math functions needs to include the current source directory. Well, math functions itself doesn't. I don't understand if I know. Yeah, I don't know if I know what this means. Like, I understand like, on a surface level, but I'm not really sure. Like, when should I use this stuff? So if you're gonna link to math functions, so assume linking, it means that whenever you have another file that is gonna include the header of a math function file, then you need to include the directories, but math function doesn't. And the hard part is understanding when is cmake running and how is it, how does it view the whole project? I think that's the thing. Public and private is also confusing. It's not hard to understand, but it's hard to think about. Like when you should use which, and I think public and private was always confusing to me. But when to use each thing. Because I don't understand from the code's point of view. Like, how does it work?
Now that we have switched our code to a more modern approach, let's demonstrate a modern technique to set properties to multiple targets. Let's refactor our existing code to use an interface library. We will use that library in the next step to demonstrate a common use for generator expressions. Goal Pilpro. Add an interface library target to specify the required C++ standard. Helpful resources Pilpro. Add underscore library. Target underscore compile underscore features. Target underscore link underscore libraries. Files to edit Pilpro. Make list.txt. Math function / make list.txt. Getting Add underscore library Pilpro. Contents. Add underscore library. Normal libraries. Object libraries. Interface libraries. Imported libraries. Alias libraries. See also. Add a library to the project using the specified source files. Normal libraries Pilpro. Add underscore library name, static, shared, module, exclude underscore from underscore all. Source. Add the library target called name to be built from the source files listed in the command invocation. The name corresponds to the logical target name and must be globally unique within a project. The actual file name of the library built is constructed based on conventions of the native platform, such as libname a or namelib. New in version 3.1. Source arguments to add underscore library may use generator expressions with a syntax $less than greater than. See the cmake generator expression 7 manual for available expressions. New in version 3.11. The source files can be omitted if they are added later using target underscore sources. Static, shared, or module may be given to specify the type of library to be created. Static libraries are archives of object files for use when linking other targets. Shared libraries are linked dynamically and loaded at runtime. Module libraries are plugins that are not linked into other targets but may be loaded dynamically at runtime using Glopen-like functionality. If no type is given explicitly, the type is static or shared based on whether the current value of the variable build underscore shared underscore lives is on. For shared and module libraries, the position underscore independent.
The thing is, I think I understand how they are saying you should use, but it doesn't tell me like when to use it. Or so I think that the way you use it, you just put the library here and then it puts module and then you put the path. Or maybe I'll do it in the same line. But I don't understand, like, so maybe this is the command that allows you to import using the, or include using the other syntax there with the, I don't know how to say that, the arrow, or yeah, let me remove these ones now. Just to see if it's gonna show anything. So it's saying, so probably when you use this add subdirectory, it creates a target already. So maybe let me think about this. So I think I'm gonna, well, I'm gonna remove this stuff here first, and then I'm gonna try to import with the name of the version instead of just putting the name of JSON. Because maybe that's the thing that is going wrong there. Because when you put the add subdirectory, it creates everything. But I still think that I would have to put the files there. So yeah. I think it's not gonna work, but just curious to see what happens. Oh, it still complains about the same thing. Oh, did I remove? No, I didn't remove. But now I'm not really sure if it's building the JSON thing or if it's gonna build. Yeah. So it doesn't find the thing. So this way that I did so far, it works if I don't have the library. Then obviously it's kind of useless. Hmm. Yeah. So let me comment this out just to see if it's working with the other stuff. 'Cause if you don't have anything else, I think it's pretty easy. And the reason why it's giving these warnings here is because I'm using a flag variable, not a flag variable, a library variable from because of the course. So in the course, he uses Linux and he uses makefile. So he was including this file here, only this header file, which is gonna contain a specification of the highest path limit for a file, I think. And then on the code, he was declaring a function that uses this path max variable. But because I'm using Windows, I had to do this stuff here, and I just used ChatGPT to see uh, the recommendation, and then I just tried a bunch of stuff, and then it worked like this, where you have this conditional statement here just checked for the operational system, and then it replaces the name of the value depending on which operational system is running the code. And then this full path is the function that it was using to. He was using another function to get the. I think he stored the path of the file on a variable. That's what the function does, I think. So because of that, I'm getting these warnings here. And I don't know how to remove them, but I don't think it matters that much because it's still working. So after it does everything, it just creates the executable here, which is the main executable for the program, which has the name of the project. So it is working if I don't have the thing there. And I can run this stuff just by the name, I think. I just call the file and then it runs the code. Now on the code, I'm getting some warnings, but the reason why I'm getting some warnings is because the way that he did it here, he uses this NASM, and NASM is uh I think is an executable, probably an executable that you put on path that is an assembler. So it's gonna take the code and then it's gonna create the machine code based on the assembly code you have, I think. And the way that he did it here, he specifies the 32-bit, but I'm using a 64-bit system. And the reason why you have to do it this way is because of the stuff that I said before, is that it's going to change depending on which operational system it is. So the way that he built the compiler and the cores is for 32-bit systems. And the reason why it matters, I think, is because on the 32-bit system is going to be the size of the row of each, not each column, like each row is going to have the 32-bit size for a 32-bit system, which is going to change the way that all the calculations are made. And also the endiness of the computer changes that as well, because it just changes the whole layout in memory, which changes how all the instructions work. So because I'm using a 64-bit and it's trying to run with a 32-bit, it just gives me a bunch of warnings. But it's still, like for the part that I want, it still works. And I'm not really, like I'm gonna have to think about this a lot more as well, because I'm not 100% sure what I want to capture, but that is still confusing to me because the code is always going to be the same, the high level code. But the thing that handles this stuff when it comes to JavaScript, for example, is going to be the browser engine. So the browser engine has a logic for selecting different instruction set architectures based on the code, and I think that's the job of the compiler, just-in-time compiler. If figures out based on with the operation, it uses the operation, communicates with the operational system to figure out what architecture the system has, and then based on that architecture, it creates different assembly code based on the JavaScript code, and then based on that assembly code, it generates the execution. But the JavaScript code is always the same. So like what I want to capture is the fundamental structure though. So I'm not really sure if I'm gonna need to think about, or maybe I'll have to do that. But then I can use this stuff here. Yeah, but this It is a question that I'm gonna have to think about. Not really sure. Because if I use this stuff here to try to visualize the other compilers, then and the question is it gonna matter that it's translating to a different assembly? Or is that not that fundamental to understand how everything is connected? I think it's not that fundamental. But I have to think about a lot more about this. But probably what I'm gonna do for now is just comment this stuff out. And then it's just not gonna try to create machine code. It's just I'm gonna do it up to the point that it creates the assembly code. So probably what I'm gonna have to do is just to look into like what are the different ways that you have to convert into assembly for the different types of systems, and what differences do that makes. Also want to understand on Python as well how that happens. Yeah, but it just runs everything and then it gives a bunch of warnings. And then it creates the file with assembly based on this file here that is compiling. So I think I'm just gonna comment this out. Yeah, I'm gonna focus on one thing at a time so I don't get too like overwhelmed with a bunch of stuff. And I think that this one also I haven't seen this. I haven't seen anyone talk about this, but so far I think that you don't need to run the clean command after you change. So the way that it was doing on the project is he would make a change and then each time he would run make clean, which would just delete all the object files and the executable, and then he would run make again and recreate everything again and then run the file again. But I think with cmake you don't do that. You just run the same command and then it automatically rebuilds everything for you. But I'm not 100% sure as well. But it looks like, oh no, it didn't work. It looks like it worked because it creates the thing. But then it complains about this. Maybe it's because that's weird. Yeah, it's complaining that it's not a command, probably. This warning shows up on the command shell or the command prompt because I think you can't just call the name of the file on the command prompt. You run files in a different way, but on PowerShell it allows you to, so I'm not really sure why it's showing this stuff here. But it looks like it's running the thing anyway, so. So let me go back to reading the documentation.
Underscore code target property is set to on automatically. A shared library may be marked with a framework target property to create a Mac OS framework. New in version 3.8, a static library may be marked with a framework target property to create a static framework. If a library does not export any symbols, it must not be declared as a shared library. For example, a Windows resource DLL or a managed C++/CLI DLL that exports no unmanaged symbols would need to be a module library. This is because cmake expects a shared library to always have an associated import library on Windows. By default, the library file will be created in the build tree directory corresponding to the source tree directory in which the command was invoked. See documentation of the archive underscore output underscore directory, library underscore output underscore directory, and runtime underscore output underscore directory target properties to change this location. See documentation of the output underscore name target property to change the name part of the final file name. If exclude underscore from underscore all is given, the corresponding property will be set on the created target. See documentation of the exclude underscore from underscore all target property for details. See the cmake build system 7 manual for more on defining build system properties. See also header underscore file underscore only on what to do if some sources are preprocessed and you want to have the original sources reachable from within IDE. Object libraries pilcrow. Add underscore library name object. Source. Creates an object library. An object library compiles source files but does not archive or link their object files into a library. Instead, other targets created by add underscore library or add underscore executable may reference the objects using an expression of the form $target underscore objects obslib as a source, where obslib is the object library name. For example, add underscore library, $target underscore objects obslib add underscore executable. $target underscore objects obslib will include obslib's object files in a library and an executable along with those compiled from their own sources. Object libraries may contain only sources that compile, header files, and other files that would not affect linking of a normal library. For example, text. They may contain custom commands generating such sources, but not pre-build, pre-link, or post-build commands. Some native build systems, such as Xcode, may not like targets that have only object files, so consider adding at least one real source file to any target that references $target_objects of glib. New in version 3.12, object libraries can be linked with target_link_libraries. Interface libraries Pilpro. Add_library name interface. Creates an interface library. An interface library target does not compile sources and does not produce a library artifact on disk. However, it may have properties set on it and it may be installed and exported. Typically, interface_properties are populated on an interface target using the commands set_property, target_link_libraries interface, target_link_options interface, target_include_directories interface, target_compile_options interface, target_compile_definitions interface, and target_sources interface. And then it is used as an argument to target_link_libraries like any other target. An interface library created with the above signature has no source files itself and is not included as a target in the generated build system. New in version 3.15, an interface library can have public_header and private_header properties. The headers specified by those properties can be installed using the install targets command. New in version 3.19, an interface library target may be created with source files. Add_library name interface. Source exclude_from_all. Source files may be listed directly in the add_library call or added later by calls to target_sources with the private or public keywords. If an interface library has source files, i.e. the source's target property is set, or header sets, i.e. the header_sets target property is set, it will appear in the generated build system as a build target much like a target defined by the add_custom_target command. It does not compile any sources, but does contain build rules for custom commands created by the add_custom_command.
Now that I think about it, he didn't go over. But the thing is, I just did the module 1 on the course, so maybe he talks about this stuff on the module 2 and 3, but he didn't go over how the. Oh, but actually C is different as well. But still, he didn't go over how the compilation process is gonna find the files in the system. And I think it's gonna be related to the operational system. It has to, because the operational system is the thing that handles the file locations, I think. So this is one problem I have as well. Because with the code that I have, if it compiles everything, but it doesn't find. I guess that's the question. Like, at what point does the include statement becomes like it finds the file, the code for the file, and does that go into the? I guess I think there is a part where he talks about this, like parsing the include thing, but I don't think he explained how does the code going to find the file and then get the code for the file to be included on the process. Or at least I don't remember. So I'm gonna review the thing again, obviously, but so I guess what I can do is just include here a standard library and see if it changes the final result. Maybe it's not working. It doesn't make sense that I would have. I'm gonna do it now, but I don't think that's the problem. Because the executable is already there, so maybe I have to change this again. Like, there needs to be a command here so it works. But I'm not really sure. So I'm gonna do this again. So it doesn't matter that much, the warning is there either way, so. I wanna see. I'm gonna copy this stuff and put here. I wanna see if it's gonna build a different assembly code when I put the include here. Because this is another thing that I have to understand. And my assumption is that Python and JavaScript is gonna be abstractions built on top of whatever C does. So the reason why C uses the header files and does the linking process is because it's more lower level. So probably on the other languages there is more logic that abstracts away this part, but is still doing the same thing under the hood. It's just linking a bunch of files based on definitions, but maybe not. Maybe it's fundamentally different. But either way, like I think this is one of the most important things to understand how it works. I think it's the same, probably. Data tax, global. Yeah, it didn't change anything. So maybe he goes over this on the other parts. I also got the code for another compiler from the same person. So maybe on the other one is more complete and it works. But either way, I have to solve this stuff first. So I have to figure out the cmake first. Then once I figure out a good way, then I think about this stuff. It's weird that it didn't give any warnings now. Huh. It's probably because of the, like now, no, it should be going over the same thing. Yeah, I don't know. I'll have to think about this.
And note, in most command signatures where the interface keyword appears, the items listed after it only become part of that target's usage requirements and are not part of the target's own settings. However, in this signature of add_library, the interface keyword refers to the library type only. Sources listed after it in the add_library call are private to the interface library and do not appear in its interface_sources target property. Imported libraries pilpro, add_library name type imported, global, creates an imported library target called name. No rules are generated to build it, and the imported target property is true. The target name has scope in the directory in which it is created and below, but the global option extends visibility. It may be referenced like any target built within the project. Imported libraries are useful for convenient reference from commands like target_link_libraries. Details about the imported library are specified by setting properties whose names begin in imported underscore in interface. The type must be one of static, shared, module, unknown. References a library file located outside the project. The imported underscore location target property, or its per configuration variant imported underscore location underscore config specifies the location of the main library file on disk. For a shared library on most non-Windows platforms, the main library file is the or dilib file used by both linkers and dynamic loaders. If the reference library file has a soname, or on Mac OS has a lc_id_dilib starting inner path /, the value of that field should be set in the imported underscore soname target property. If the reference library file does not have a soname, but the platform supports it, then the imported underscore no underscore soname target property should be set. For a shared library on Windows, the imported underscore implib target property, or its per configuration variant imported underscore implib underscore config specifies the location of the DLL import library file .lib or DLL.a on disk, and the imported underscore location is the location of the DLL runtime library and is optional, but needed by the target underscore runtime underscore DLLs generator expression. Additional usage requirements may be specified in interface underscore properties. An unknown library type is typically only used in the implementation of find modules. It allows the path to an imported library, often found using the find underscore library command, to be used without having to know what type of library it is. This is especially useful on Windows where a static library and a DLL's import library both have the same file extension. Object references a set of object files located outside the project. The imported underscore objects target property, or its per configuration variant imported underscore objects underscore config specifies the locations of object files on disk. Additional usage requirements may be specified in interface underscore properties. Interface does not reference any library or object files on disk, but may specify usage requirements in interface underscore properties. See documentation of the imported underscore and interface underscore properties for more information. Alias libraries pilpro, add underscore library name alias target, creates an alias target, such that name can be used to refer to target in subsequent commands. The name does not appear in the generated build system as a make target. The target may not be an alias. New in version 3.11, an alias can target a global imported target. New in version 3.18, an alias can target a non-global imported target. Such alias is scoped to the directory in which it is created and below. The alias underscore global target property can be used to check if the alias is global or not. Alias targets can be used as linkable targets and as targets to read properties from. They can also be tested for existence with the regular of target subcommand. The name may not be used to modify properties of target. That is, it may not be used as the operand of set underscore property, set underscore target underscore properties, target underscore
I
link
think I
underscore properties, etc.
shouldn't
The
use
alias target
this
may not be
one.
in
It seems like this one is more for when you have only one file and it's the file with these extensions here. So it's probably not this one that I have to use. But it's another thing that it doesn't make like, it's not that it doesn't make sense, it's that I'm not clear about is which way you should go about it. Because if I'm gonna put the source, like the C files on there, if I'm gonna put the C files here and then I'm gonna put them here and it's gonna create the executables, why do I need to specify the header files for each thing? Like, doesn't this stuff already do that? So I guess it's just one of the points of confusion that I have. It feels like it's kind of all over the place, so it's hard to know. And I think that's the downside of the not having this standard. So obviously there's trade-offs for everything. So That's probably why on Python and JavaScript they moved to the standard because it feels much better. But maybe there is a benefit for doing like this because it gives you more flexibility, but at the same time, I'm not really sure. It just feels like it's worse, to be honest. But obviously, I don't have experience, so maybe like there's some cases probably where it's better, like for everyone to be able to do their own thing.
Target underscore link underscore libraries pilpro. Contents. Target underscore link underscore libraries. Overview. Libraries for a target and or its dependents. Libraries for both a target and its dependents. Libraries for a target and or its dependents. Legacy. Libraries for dependents only. Legacy. Linking object libraries. Linking object libraries via $target underscore objects. Cyclic dependencies of static libraries. Creating relocatable packages. See also. Specify libraries or flags to use when linking a given target and or its dependents. Usage requirements from linked library targets will be propagated. Usage requirements of a target's dependencies affect compilation of its own sources. Overview pilpro. This command has several signatures as detailed in subsections below. All of them have the general form. Target underscore link underscore libraries target. Item. The name target must have been created by a command such as add underscore executable or add underscore library and must not be an alias target. If policy CMP0079 is not set to new, then the target must have been created in the current directory. Repeated calls for the same target append items in the order called. New in version 3.13. The target doesn't have to be defined in the same directory as the target underscore link underscore libraries call. Each item may be a library target name. The generated link line will have the full path to the linkable library file associated with the target. The build system will have a dependency to relink target if the library file changes. The name target must be created by add underscore library within the project or as an imported library. If it is created within the project, an ordering dependency will automatically be added in the build system to make sure the named library target is up to date before the target links. If an imported library has the imported underscore no underscore sunnamed target property set, cmake may ask the linker to search for the library instead of using the full path. For example, /user/lib/libfoo.so becomes lfoo. The full path to the target's artifact will be quoted /escape for the shell automatically. A full path to a library file. The generated link line will normally preserve the full path to the file. The build system will have a dependency to relink target if the library file changes. There are some cases where cmake may ask the linker to search for the library. For example, /user/lib/libfoo.so becomes lfoo, such as when a shared library is detected to have no sunnamed field. See policy CMP0060 for discussion of another case.
I'm just gonna go to the directly to the thing that I want, which is the dependency. And I think I'm going to spend time now. Like maybe I'll look at this stuff later. Just gonna spend some time with ChatGPT and maybe trying to research on. I want to clarify how exactly does C finds the modules. And also I'm reading another stuff about interpreters, but I also think that he didn't talk about like this process of finding the other files. So it's something that I have to clarify. Because that's one of the links between the compiler and interpreter and the operational system. I think the main points of connection is just the instruction set architecture, and it's going to be the stuff with the files. But the stuff with the files, in my mind, has to come before the assembly, like the code becomes assembly. But I'm not really sure. Maybe it depends on the case, because like in the way that it would make sense in my mind is that as you parse the code, you create the lexers, and then from the lexers you create the abstract syntax tree. The abstract syntax tree is going to be the thing that allows you to create more meaning by navigating the tree and creating expressions from the lexers. And then once you do that, then at that stage it feels like to me it would make the most sense to handle the import system, because then, but then like it is kind of confusing because like how would you go about building the code from that? Maybe it's like a linked list in the same way that scopes exist. Like the scopes are a linked list between different environments. So maybe with import, it's the same way that where whenever it encounters the import statement, it just links to another scope and then it continues to parse the code. And then at the end, you have just the like the copy paste code, like as if it's being written only one file in one file. That would be the thing that makes the most sense. But then how does the process works? Because for finding the file, we would have to communicate with the operational system, I think. Or in cases where you have the main one that I'm most interested about is the absolute imports, both in. But I think in Python it's kind of easier because it's always going to be, maybe in JavaScript is the same. Because in Python it's always going to be on the package. I forgot the name of the thing. But there is a standard file where all the packages are stored, the external packages for Python. So thinking Python, the way that it works is, but it does communicate with the operational system, and then the operational system finds the path. It looks for the project on the path. And I think in JavaScript it's going to be the same with node modules. Or just gonna, but in JavaScript there is the case where you can put like you can actually put the link on GitHub, I think, for the project. So in that case, I think it's more like in the same way that is happening here with cmake, where there's some logic under the hood that creates a server and a client, and then that logic is gonna make requests on the internet to find the project and then download the project. and then structure everything. And I think this case is one that I've seen a lot on Solidity. So I think that's Solidity that's probably like similar to that, but then this is the main thing that not the main thing, but one of the fundamental things that I want to understand.
To compile a project that depends on an external library like Jansen using cmake, you need to follow several steps. Here's a step-by-step guide. Clone or download the external library. First, make sure you have the external library, in this case, Jansen, on your system. You can either clone the repository or download a release from the library's GitHub page. Bash copy code clone https://github.com/jansen.git. Create a cmake list.txt file for your project. In your project directory, create a cmake list.txt file. This file will describe how your project is built. Here's a simple example. Make copy code cmake _minimum_ required version 3.0. Project your project name #add your source files @_ executable your project name main.cpp. Specify the include directories for your project include _directories $cmake _source _dir/jansen/include. Specify the libraries to link against target _link _libraries your project name $cmake _source _dir/jansen/libjansen.a. In this example, replace your project name with the name of your project and adjust the paths to the Jansen library as needed. Build your project. Now, you can build your project using cmake. Run the following commands from your project's directory. Bash copy code enter build cd build cmake. Make. This will create an executable for your project, and it should link against the Jansen library. Run your project. After successfully building your project, you can run it. Bash copy code // your project name. Please note that the above example assumes that Jansen is already built as a static library .a file and placed in a directory within your project. If Jansen provides a cmake configuration script, cmake list.txt, you can include it in your project instead of manually specifying include directories and libraries. Make sure to refer to Jansen's documentation or GitHub repository for any specific build instructions for your platform and desired configuration. Also, make sure you have cmake and a C++ compiler installed on your system. Adjust the cmake list.txt file and build process according to your project structure and dependencies. Free research preview. ChatGPT make.
It's crazy how good ChatGPT is. I think his own build. It's probably not gonna work, but like it's still like the more that I think about it, like I use ChatGPT a lot, and it happened so fast. Like a lot more than searching for, like using search engines. But at the same time, it's very concerning. But I think that the most likely way for this to evolve is that's gonna be like a gradient between private and open source, and it's gonna be instead of having search engines, it's just gonna be large language models. But then, like the issue is like it's kind of similar to code as well. Is that search engines feel a lot like it feels that you are a lot closer to the results, but maybe that's just an illusion because like it gives you the false sensation of control. I think search engines because they're still selecting which results are gonna show, but it feels more like you're capable of like finding the path yourself. But with large language models, it's just a black box. So the control is fully on the large language model. So you have to trust that whatever output is giving you is the correct one. So I think that probably because of this reason, search engines are never gonna go away, I think. Because it's just different. But there's probably a middle way between the two. I think that's probably where it's gonna go. Like with Bing, where you have the large language model that is embedded on the search engine, and then it just gives you stuff. Builds, JSON. And this has the header files for the thing. I think I'm gonna erase. Maybe I'll leave this one here because it doesn't matter. It's just the way that it works. I think is that the first time that you run the cmake stuff, the command that is gonna build everything. So this command here. After the first time they run, it creates a cache file that is gonna store the configurations. I think. So when you run the build command, it does everything based on the cache files. So for example, here, I think that this command only runs on the first time. And then once it creates the cache, it's not gonna rebuild the library again. So it doesn't matter if I leave here. And I think this command is just finds the cmake list file inside of whatever path you put here, and then it runs that cmake list for that project. And then that command is gonna build everything for that project. So I think it doesn't matter if I just leave there. So it's telling me to do this includes, to include the directories, which is probably gonna is the thing that includes the header files. And then it's telling me to link the A files. So apparently the .a extension is for static library. So it's gonna be this path. Let's see if this works. Oh, your project name somewhere. Oh, here. Uh, projects. Yeah, but I didn't have to put the thing here, the command. There's another question I should ask is, I have to spend some time thinking about good questions to ask ChatGPT, and then it's probably gonna help me clarify. So the questions is more about when should I do each thing, rather than how each thing works. So maybe I should just ask that. And this is the thing about large language models, which is the double-edged sword. That is gonna, but it's the same thing. It's the same thing that happens with search engines, but it's a different way. It's just I'm never gonna know fully if it's giving me like 100% correct or not. And the difference between search engines is that you can go into multiple different sources and see. So it's like, I think the question is surface over depth. So large language models is like you're encapsulating all the information into one concept, let's say. And then from that you extract information. And then search engines is more like you're exploring the surface. And then from that surface, it allows you to jump like in a graph network. So they're both graph networks, but the interface is different. Yes, obviously one thing that would be nice is to be able to visualize the weights and biases that are going to be that are activated at each time, which is pretty crazy to think about as well. And it's going to be very complex. I think that's like when you put the command, it's just the thing is I'm not really sure how it works, like the specifics of it. But yeah, I think you train first, and then with that the train, like the model you are interacting with is already a fixed set of weights and biases, unless you use reinforcement learning, I think, with feedback or something like that, where you're just constantly retraining the model based on new inputs. But I think the current models are obviously not gonna be like they're not the final thing. Uh, so in the state that it is, but even in the state that it is, I think it would be nice to be able to visualize the as you put the input to visualize, highlight what is actually what weights and biases are firing to construct the response. So I think what I'm gonna ask is just when should I use each command? Maybe I should ask first to give me an overview of. I think that's probably better. I'm gonna do like a mix of both things. I'm gonna capture. How do I find all the commands that are related to libraries or external packages? Then make a list of them. Then tell ChatGPT to give me an overview of each one. Once I have the overview, then I can tell me to say the trade-offs of each one or when should I use each one. That's probably the best thing to do. So I wonder if I can find a page that has all the commands. Yeah, maybe these ones, module and packages. I'm just gonna not gonna look into all of them. I'm gonna try to figure out which ones are probably the most relevant based on the videos that I already watched. Then yeah, I'm gonna put the names here and then use ChatGPT to try to clarify. So I'll be right back. something about another thing. Or because of the way that I wrote this stuff. Damn, it worked. If this works, then I'm just gonna forget about this. Because obviously I wanna focus on the stuff that I'm building. It's still like a lot of different stuff to. At the same time, I wanna make sure that understand well how cmake works because uh, you will only have to understand it once, and then after that it becomes easier. So I want to make sure I understand it, but at the same time, it's one of those things that is kind of a pain in the ass because I could be using all this time to actually solve or try to solve the stuff that I'm trying to do. And what I'm gonna do is just use this library here. If I can use this library, then I'm just gonna study the documentation and then try to implement the functions from the library in order to convert the graph that I'm building to JSON. So I can save everything on the JSON file and then I can use the JSON on the front end. So first I'm gonna do it manually, and then once I figured it out, like once I optimize the feedback loop system, then I'm going to see if I can make the network connections, and then I don't have to save the files, I just pass the data. But like this is one thing that I've been thinking about as well, which I've seen on Twitter, I think a video of Carmack saying that it's not a good idea to use multiple different languages. If you can, you should only use one language for the project. And I agree with that logic, I think, because obviously everything becomes harder if I'm using more languages, like when it comes to scaling as well. So I've been contemplating a lot on what I should do about this because I think I have to use at least two languages, one for the backend, one for the front end, and then front end is obviously JavaScript, backend. I'm thinking about using Python, but this is the problem, is that but for now, I've been thinking that it's probably best this way, where the way that I'm thinking about it is just I have the JavaScript on the front end, then Python works kind of like a controller. So I send the request through a Python API. Then with the Python API, it handles the logic of which compiler is going to be used. And then because if I'm able to structure this in the correct way, then all of the compilers are gonna have roughly the same logic. Like they're gonna build the same types of graphs. The only thing that is gonna change is which kind of compiler I'm using for each kind of language. So based on that, I can just like create use Python as kind of like a router that calls the function in C for whatever compiler I have. And I think that probably C is a better language than Python to build the thing, but maybe not. Maybe this is the stuff that I'm not 100% sure. I think it might be better on C because there is more likely that I'm gonna find other compilers for other languages. So like C is lower level, so there's higher chance that is a common denominator between other languages. So the structure of the code is gonna be similar if I do it in C rather than in Python. If I figure out in Python, I'm gonna have to rethink about the whole thing for each language. If I do it in C, I already found the Python interpreter is written in C. I already found one for JavaScript as well, probably for other languages. If I don't find it, it's gonna be relatively similar to translate the logic for parsing the code. That's the reason why I think probably C is better. But then it leaves me with this issue that I'm gonna have like 3 different languages. So I use Python to select, and then based on whatever interpreter it is, it creates the graph and then sends the JSON format to Python again, and then from Python I send it to the front end, and then the front end builds the visualization based on the data structure. I've been also been thinking about maybe I think I'm gonna say this later once it's time to work on the stuff that I'm thinking about. Yeah, so maybe it worked. So I'm gonna try to run, and then if it works, I'm gonna. So okay, it seems like it works. So I'm gonna try to see if I can just use a function from the. I have these functions here from the library. Nice. Okay. So maybe I forgot about everything. So I think what I'm gonna do is just the stuff that I was talking about before. But I'm really happy about that. It seems like it is working. Maybe shouldn't be like because sometimes it seems like it worked, but there's something going on. So I think the only way I'm gonna know is if I after I build this stuff. But I don't think I'm gonna do that now. I'm gonna. It's likely that it is working. So and translating the thing is gonna be like another challenging thing. So I'm gonna have to spend some time thinking about it and doing nothing. So I don't think it's better to do that now. It's probably better to spend some time thinking off stream, and the next time that I stream, I'm probably gonna have a better idea of how to build. Yeah, I should probably what I'm gonna do is probably test off stream to see if I'm maybe I should console log here, like print off the stuff to see if it's working or not. Because the other thing that is, I haven't tested the other part as well. I just assume that it's correct because it's compiled and it executes. But to see if it's actually building the graph in the way that I'm imagining in my mind, I think I have to printf here at some point. At least that's what I'm used to doing on the other languages. So the way that I'm doing right now is just the simplest way possible, just to so I can build at least one graph to see how it looks. But what I'm doing is just building nodes from tokens. So I pass the graph inside of the function, and then when it's creating the tokens, I pass the token inside of this function, and then I convert the information from the token to the node. And if that works, I'm gonna change the logic here to capture whatever essence of the thing I want to capture. So I can do like different radios based on frequency or stuff like that, or change the color based on some logic. So, but obviously, and this is the part that I'm talking about, where the way that I imagine that is going to evolve probably is that I'm going to have like several different standards of stuff that is probably useful. But the only way I'm going to be able to know if the standards are useful or not is after I use the visualization to try to understand other code. So this is the kind of difficult thing because I have to test this on the front end to see if the graph is useful or not. And then once I see if the graph is useful or not, then I can come back on the code and think about the logic again to optimize this. But right now, the only thing that I'm doing is just getting the sval, which is kind of the value that token has. When is a identifier or a keyword, I think, and if it is a number, it has other specifiers, which I'm probably gonna get later. So I receive the token, translate into node logic, and then after that, I'm just connecting them sequentially based on another function, I think, at this function here, which is also going to be another challenging part. But right now, the easiest way that I found is just to, like, I get one node, because of the way that the vector peak works, I think it's, like, when you create the vector, it's just place on memory, and then it's just going to place blocks of memory for each thing that you want to, you put on the vector. But the way that you loop over the vector is kind of different than I was used to in Python and JavaScript. Is that this way it looks like you create a pointer, and then from the pointer you get the information on the vector. But then the pointer is kind of like a global variable where it doesn't reset after the loop. So in other languages you can do like a for loop, and then after you do that for loop, it doesn't interfere with other for loops you're gonna do later. But here, apparently based on the way that he created this library, when you use this function, it just moves the pointer like throughout the execution of the program. So here, I'm setting the pointer to the other node, the next node, every time you call this. but I'm not 100% sure if that's how it works because I haven't tested. But I think that's how it's working on my mind. So I just get one node and then the next node, and then I connect them sequentially based on the order that I created them here, and that I append on the graph. Then after I create all this stuff and I have the nodes and edges on the graph structure, I'm gonna pass the graph structure to this function, like at the end of the compilation process, and I'm going to loop over the nodes and edges, and I create, like, I'm gonna parse the information from C to JSON. And that's why I'm trying to use this library here, because they probably wrote everything already, like, in the best way, and it's gonna be better than me trying to figure out myself again. Which I might do as well. I might spend some time looking at the source code. I'm probably gonna do that, so I understand like how they went about doing that. But I think that the way that you do it is just string formatting. So you just get the information from structs and vectors, and then you do some string formatting to being the way that you want the information to be. Then you open a file, and then you write the bytes to the file. So you're just gonna write the string to the file using the functions in C, which call the operational system to find the location of the file based on the file path, and then writes the information on disk to the file. And then once you have the file, you can just use the JSON. Yeah, so that's what I'm thinking. But it's gonna be better, I think, to figure this stuff out off stream, to how to actually build the information, or like try to test this later. So what I'm gonna do now is just search for the names here on cmake, and then I'm gonna try to use ChatGPT to clarify my mind on when I should use each thing. But hopefully this way is working now with the information that it gave me there. So as far as I understand, I think it is what I'm thinking of. Probably I should use targets, because I've seen one video that they recommend to use target now instead of just include, because it seems like it is more recent and it's better, but I'm not really sure why. But it is the stuff that I was thinking about, I think, where this one is kind of like using this flag variable in when you use directly the makefile, which just allows you to specify where the header files of the thing are. And the header files are the stuff that has the declaration of the functions. So the declaration is just the name of the function and the arguments. It's kind of like a signature of the function. And then from the declaration, the linking process is going to find where the definition of the function is, which is actually the code that the function itself is going to execute. So it's kind of like creating a hash between the declaration of the function and the definition of the function itself. So the first thing that the linker, not really sure if, sure if it's the linker or the compiler, but in one of these parts, the thing looks for the symbol that is the function declaration. Then based on that symbol, there's going to be a location in memory that contains the execution of the definition of the function. So in order for the compiler to know, you have to specify where the header file is. So it finds the declarations. And then based on declarations, it goes to the execution. So I think that this is the part where you specify on the cmake where the declarations are, the header files are. But I'm not sure. Maybe I should erase this and see if it works, because this one is supposed to be including everything from the top of the project. So I'm not really sure if that's worth necessary or not. This one I don't understand really well, but I assume that it's just finding the file here, and this is the file that has the resulting compilation of the library. So after you compile the library itself, the JSON library itself, it creates this file here. And this file probably has information of that tells the linker where to find the definitions for the headers. So you have you specify where the headers are, and then here it's a file that specifies how to go from the header to the function definition. Maybe, but I'm not 100% sure. So this is what I have to clarify. Maybe I think the first question I'm gonna ask is about this thing here. I'm not sure if any of this is clear or not. It's a lot more confusing than the other languages. And then uh, this one I think is the easiest one to understand. It just finds the cmake list file for the other project and then just runs the cmake list and builds everything. But also it's kind of there's still a lot of questions because I don't know exactly what command is using to build this stuff. Because on this one I can specify the generator. Just gonna be which compiler is gonna use which compiler. You're telling the cmake thing to select whatever compiler you want when you pass the G flag. So I assume that when you put this stuff here, it just uses whatever default compiler you have. But then it brings more questions because like if this one is using but maybe not. I think that what's happening is that they all use the same compiler you specify on the main command you're running. I think that's probably what's happening. So in this case, you would use the same GCC compiler to build this library here because I specified on this command. And this command is the one that is running this, is using this one to build the process in the beginning, to build all the cmake files. So I think that's what's happening probably.
Target underscore link underscore libraries is a cmake command that specifies the libraries that should be linked to a target, typically an executable or a shared library. When building a cmake-based project, under the hood, it fundamentally does the following: library linking. When you use target underscore link underscore libraries, cmake sets up the necessary build system rules to link the specified libraries with the target. This means that during the compilation and linking process, the object files from the specified libraries, in your case, the A files, are combined with your target's object files to produce the final executable or library. Library search paths. Make also sets up the necessary search paths for the linker. It ensures that the linker knows where to find the libraries you've specified. In your example, when you use $cmake underscore source underscore dir slash jansen slash libjansen.a, make informs the linker to look for the libjansen.a library file in the specified directory. Transitive dependencies. Make is smart about handling transitive dependencies. If a library you're linking against depends on other libraries, cmake will also link those dependent libraries automatically. This ensures that your project has access to all the necessary symbols and functions from both the library you directly link and its dependencies. Regarding A files, they are static library files in the Unix-like world, including Linux. Here's what they fundamentally do. Compilation units. A file contains compiled object files, .o files, that were produced during the compilation of a library's source code. Each object file represents a compilation unit, a source code file that has been. Free research preview. ChatGPT may produce inaccurate information about people, places, or facts. ChatGPT August 3rd version.
Yeah, so I think what is happening is that the .a file is like all the .o files combined. That's probably what is going on. So the .a contains the information for all the .o files. So when you put the file there, it just finds this file, and this files has the information for all the .o files, and the .o files are the ones that are used on the linking process. So I want to clarify more about which one. It is definitely linking first, obviously, because otherwise how would you compile if you don't link? So I think the first thing that happens is just finds all the header files and then like links the declaration with the definition. And then after that, it compiles all the code. But I want to clarify how that works.
Static linking. When you link your program against a static library using target underscore link underscore libraries with a file, the object code from the library is physically included in your program's binary compile time. This means that the code from the library becomes a part of your executable, making it self-contained. Your program doesn't rely on external dynamic libraries. So files when it runs. Advantages and disadvantages. Static libraries have advantages like predictable behavior, since they include all dependencies, improved performance, no dynamic linking overhead, and independence from system libraries. However, they can result in larger executable sizes and can't be easily updated or replaced without recompilation. In contrast, dynamic libraries. Files on Unix-like systems are linked at runtime and allow multiple programs to share a single copy of the library. They are typically smaller and can be updated without recompiling programs. The choice between static and dynamic linking depends on your project's requirements and the trade-offs you're willing to make.
Hmm. Let me read this again.
1. Target underscore link underscore libraries is a cmake command that specifies the libraries that should be linked to a target, typically an executable or a shared library. When building a cmake-based project, under the hood, it fundamentally does the following library linking when you use target underscore link underscore libraries. Cmake sets up the necessary build system rules to link the specified libraries with the target. This means that during the compilation and linking process, the object files from the specified libraries, in your case, the A files, are combined with your target's object files to produce the final executable or library.library search. Cmake also sets up the necessary search paths for the linker. It ensures that the linker knows where to find the libraries you've specified. In your example, when you use $cmake underscore source underscore dir slash jansen slash libjansen.a, make informs the linker to look for the libjansen.a library file in the specified directory. Transitive dependencies. Cmake is smart about handling transitive dependencies. If a library you're linking against depends on other libraries, cmake will also link those dependent libraries automatically. This ensures that your project has access to all the necessary symbols and functions from both the library you directly link and its dependencies. Regarding .a files, they are static library files in the Unix-like world, including Linux. Here's what they fundamentally do. Compilation units. A file contains compiled object files, .o files, that were produced during the compilation of a library source code. Each object file represents a compilation unit, a source code file that has been compiled into machine code. Static linking. When you link your program against a static library using target underscore link underscore libraries with a file, the object code from the library is physically included in your program's binary compile time. This means that the code from the library becomes a part of your executable, making it self-contained. Your program doesn't rely on external dynamic libraries. Files when it runs. Advantages advantages and disadvantages. Static libraries have advantages like predictable behavior, since they include all dependencies, improved performance, no dynamic linking overhead, and independence from system libraries. However, they can result in larger executable sizes and can't be easily updated or replaced without recompilation.in. Contrast, dynamic libraries, .so files, on Unix-like systems, are linked at runtime and allow multiple programs to share a single copy of the library. They are typically smaller and can be updated without recompiling programs. The choice between static and dynamic linking depends on your project's requirements and the trade-offs you're willing to make.
I think I'm gonna spend at least like, just some more time here. Then I'm gonna stop streaming and figure this, like study this other stuff and test the other stuff off stream. I'm probably gonna test to see. First, I'm gonna print the graph there to see if it's working. Then I see if the JSON. Probably the best thing to do is just try to create a simple file first, because then I'm gonna obviously know if I create the JSON file if the library is working or not. So
The C compilation process is a multi-step process that transforms your C source code into an executable program or a shared library. It involves several stages, including preprocessing, compiling, assembling, and linking. The linker plays a crucial role in the final stage of this process. Here's a simplified overview of the C compilation process and the role of the linker. Preprocessing. The first stage is preprocessing. It involves handling directives starting with hash, like hashtag include and hashtag define. The preprocessor expands macros, includes header files, and performs conditional compilation.in. Your example, when you include an external module like slib.h with hashtag includes slib.h, the preprocessor searches for this header file in the standard system directories, for example, /user/include on Unix-like systems. It may also look in directories specified by the iflag during compilation. Compiling. After preprocessing, the compiler translates the preprocessed source code into assembly code or intermediate machine code, depending on the compiler and target architecture. This step results in one or more object files, for example, files, one for each source file. The compiler performs syntax checking, type checking, and optimization during this stage. Assembling. If the compiler output is in assembly code format, the assembler converts it into machine code in the form of object files. On many systems, this step is often combined with the compilation step, and you directly get object files as output. Linking. The linker's job is to take all the object files generated during the compilation and assembly stages, along with any external libraries that the program depends on, and combine them into an executable or shared library. The linker resolves external module dependencies by searching for the required functions and variables in the object files and libraries. This process includes the following steps. A. Symbol resolution. The linker identifies symbols, functions, or variables that are referenced but not defined within the current object file. B. Symbol table. Each object file and library contains a symbol table, which lists all the symbols it defines. The linker uses these tables to find the missing symbols. C. Symbol resolution algorithm. The linker searches through the object files and libraries in a specified order, often left to right, to locate the symbols. It may search system libraries, user-defined libraries, and finally, the current object file. D. Error handling. If the linker cannot find a required symbol, it produces a linker error, indicating that there's an unresolved external reference. Once all dependencies are resolved, the linker combines the object files and libraries into the final executable or shared library. The linker also assigns addresses to symbols and resolves relocations, ensuring that function calls and variable references are properly linked to their definitions. Output. Finally, the linker produces the executable program or shared library that you can run. In summary, the linker's primary role is to resolve external module dependencies by searching for missing symbols in object files and libraries. It ensures that all required functions and variables are correctly linked together to create a functioning executable. The process involves symbol resolution, symbol table lookup, and error handling in case of missing symbols.
it's actually not that hard, I think. I think that I'm probably confused about the external modules in when you're using JavaScript, where you can put like I forgot the name of the thing, but this symbol here, and then the name for like GitHub, whatever. I'm pretty sure on Solidity it is like this, But I think the only thing that is happening is just downloading the library first, or you have to have the library downloaded first, and then the only thing that it does is just looks for the path in the thing. But Solidity is gonna be different because obviously it's on the blockchain, so I think that for that case it is different. So I have to remember how it works because I think that the blockchain is a stack virtual machine, if I remember correctly, and then the blockchain does the computation, but I don't think it has like a directory. So probably like not sure if it's a good way to think about it, but one way to think about it is that it is kind of like a decentralized computer, but I don't think that it has its own file path. I remember that there is the other stuff that is IPFS, I think, which is another system for storing information in a decentralized way, somewhat decentralized way. So I think that's what is going on, but I don't remember the specifics really well. And I do remember that on the course, there's a moment where he talks about this as well. Like he parses this stuff, and I believe he parses as a string. So he looks for this character and then creates a buffer, and then inside of the buffer puts the other stuff, and then looks for the closing character again. And so it sounds more complicated than it is probably. So the way that it probably happens, because I think that he goes in depth into the other parts of the course, and I don't remember really well. I just remember vaguely the part where he creates the lexers and some parts of the parser. I remember for the include statements and the macro statements. But probably what is happening is just like translating the information into an abstract syntax tree, and then from the abstract syntax tree, it just uses the file system probably to. But then like the question is which file system? Maybe this is the is on the. Maybe I should ask this to clarify. Like, I'm gonna ask for other languages as well. Yeah, I don't think I'm gonna spend any time today more on cmake. Just gonna spend some time thinking about this other stuff. Hopefully, the solution that ChatGPT gave there, and it seems to be working. Hopefully, it is working, and I don't have to think about this for now. And I can just use this one so I can go back to trying to solve the actual problem and parsing the JSON. This is the last, hopefully, the last step, because once I'm able to parse the JSON now, at least I'm gonna have one graph that I'm gonna be able to visually see like what is happening on the compilation. And I think that's when is when it starts getting interesting, because I'm gonna be able to like see, like visualize on the graph the information, and then I'm gonna be able to start thinking more about how can I structure everything. So I think like this is the final part where it's still kind of annoying. So this is the last thing that I'm gonna ask, and I'm gonna stop here.
The path resolution for finding the files included via hashtag include directives primarily occurs during the preprocessing stage of the C compilation process. Here's a detailed explanation of how this path resolution works. Preprocessing stage when you write hashtag include header.h or hashtag include header.h in your C source code. You're telling the C preprocessor to include the contents of the specified header file in your source code. The preprocessor begins by searching for the header file in a specific order. A system include directories. It first looks in the standard system directories, which are predefined paths where system headers, like studio.h or lib.hr, located. These directories are typically specified when the C compiler was installed or configured. On Unix-like systems, these directories are often found under /user/include or /user/local/include.b. User-defined include directories if the header file is not found in the system system directories. The preprocessor checks any additional directories that you've specified using the icompiler option. For example, you can use i/path/ to slash your slash includes to tell the preprocessor to search in /path/ to slash your slash includes for included headers.if. The header file is found in one of these directories. The preprocessor replaces the hashtag include directive with the contents of that header file, effectively pasting the code into your source file. If the preprocessor cannot find the specified header file in any of the directories it searches, it will generate a compilation error indicating that the file could not be found. You'll see an error message similar to fatal error. Header.h, no such file or directory. Note that when you use angle brackets, header.h, the preprocessor only searches in system directories, whereas when you use double quotes, header.h, it searches in both system directories and the directories specified by flags. In summary, path resolution for finding included header files primarily occurs during the preprocessing stage. The preprocessor searches for header files in a specific order, starting with system directories and then checking user-defined directories specified by flags. If the header file is found, its contents are included in the source code. If not found, the preprocessor generates a compilation error. This mechanism allows you to include external header files and dependencies in your C code without needing to specify the full path of those files in your source code.
I think that standards are part of the consensus algorithm for a network. This is some stuff that I've been thinking about more and more. It's becoming more clear in my mind, I think. Like they're directly correlated with the variance of data in space-time, I think. Because if you think about it, every time that you have to, like, you want to scale something, and there's gonna be variance, like, there's always a trade-off, but the question is at what point does a standard make sense? And I think it's directly correlated with the variance of data. Or maybe inversely correlated. So more variance, the more need for a standard. So like it balances things out. Not sure if that makes sense. But I know that for now I can't think about like a fundamental thing. But I know there is something there, but I just can't clarify yet. Like there is a correlation with the way that the standards work and the way that the network of computation works. Because obviously from the conceptual level, it's easy to understand like the reason why you create standards, but I think there is a fundamental part of physics there that's like based on certain variables on the system, it starts like there's a threshold or where it makes sense to create a standard. It's like a synchronization mechanism on the network. The last question I'm gonna ask is about Python or JavaScript. Maybe JavaScript first, then Python. But I think that they are probably the same because you have to load the libraries anyway first. So in both of the languages is gonna be the code is gonna. I think that the question is not this. Is like the question is how does the language communicate with the operational system to actually find. How is the communication? I think this is more the stuff that I want to know. is whether or not there is a standard, because you can think about it like easy way to think about it is that when you're creating the compiler, you create the logic yourself, so you select which library you're gonna use to build to. I guess it depends on the language, because the language are gonna have the standard library that is gonna have the functions that communicate with the operational system that get the read the files. So I guess the answer is just gonna be use whatever function you have for that language to find the files. And then the algorithm is arbitrary because it doesn't matter. You're just finding the path based on the parser. So I guess that's the answer. So I think that probably the only point where a standard is necessary because of the differences in architectures is going to be the instruction set architecture standard. So is at the moment that the high level language becomes assembly, because the assembly is the main part where the the architecture of the hardware matters, because the commands are arbitrary. And I think that's the thing. Like, this is the stuff that I'm talking about. Standards is that it's interesting to think about the fundamental thing, because they're always going to be subjective to some degree. Because, like, in one way to think about it, there is nothing fundamental that is going to determine that some set of structure of binaries is going to be one command or another, like the name itself. So you're projecting the concept you want to encapsulate the state of the electromagnetic field that is going to hold the information for what you want. And I think that's the fundamental like part of the social structures as well, because it is related to language. So in a way, it's a self-fulfilling prophecy, because the construction of symbolic representation that the society has, that is building the code, is going to project the concepts it has into the hardware. But there is a fundamental part there, which is the data that creates the binary. So the data is always going to be the same, but the construction of meaning from that data is going to be different depending on the computation of the network, I think. And that's what builds the symbolic representation. But it is kind of like the self-fulfilling prophecy of the first time of the compilation process, because in this bootstrap part is the part that is interesting, I think. Because in the first place, it's going to be arbitrary, and then it's going to use the commands to create the rules that are going to create the compiler, and then it becomes a self-fulfilling prophecy. But because like it comes from outside of the compilation itself, because it already comes from the society, but there is some stuff, there has to be some fundamental property of the laws of physics that creates the symbolic representation of human beings. So the way that language in human beings evolved in the first place. And I think that's stuff that is related to the grammar, to terminals and non-terminals, that comes from Noam Chomsky, I think. I'm not sure if I'm saying his name correctly, but I think this is the kind of stuff he was probably thinking about when he created this stuff about terminals and non-terminals and grammar. And I believe that the standard is probably directly related to that, because the standard is necessary in order to contain the variance of the. It is a problem of scale. The more you scale, the differences in computation of different structures are going to have different symbolic representations of what the thing means. So the standard is the synchronizing mechanism between different symbolic representations of things. So it's related to like is the gravitational force of how you keep the flow of information on. You make the flow of information scalable between different architectures of symbolic representation. So the interesting question is that like at what point, what are the points of connection and how does it work? Because if it is fundamentally grounded in the laws of physics, then that means that you can probably calculate what would be the optimal time to create a standard. And then, but then like, the other thing that I think is interesting is like it's going to be subjective. So is there a better way to create a standard or not? So because you can choose whatever standard, like is there anything that says that, for example, creating a load command instead of whatever other name is going to be better or not?
The compilation system, including how it looks for system directories when searching for included header files, is platform-specific and can vary between different operating systems and compilers. There are, however, some common conventions and standards that many compilers follow. Below, I'll provide an overview of how this process generally works. Operating system conventions. Operating systems often have specific conventions for where system header files should be located. For example, on Unix-like systems, for example, Linux, system header files are typically found in directories like /user/include and /user/local/include.on. Windows, system header files are often located in directories like c:\program files, x86 /Microsoft SDK'/V10.0a/include for Microsoft Visual Studio. Compiler defaults. Compilers often come with default search paths for system directories, which are predefined based on the target operating system. These paths are set when the compiler is installed or configured and are part of the compiler's standard behavior. Environment variables. Some compilers and build systems allow you to specify additional system include directories using environment variables. For example, in GCC, you can use the cp8 environment variable to add additional include directories. Command line options. You can often influence the search for system directories by using command line options when invoking the compiler. For example, the I flag allows you to specify additional directories for the compiler when looking for header files. You can also use isystem for system directories to avoid treating warnings in these directories as errors. Compiler specific behavior. The specifics of how a compiler looks for system directories and handles included header files can vary between compilers. For example, GCC and Clang have some common behaviors, but they may also have compiler-specific features and options. As for whether this process is arbitrary or standardized, it's a mix of both. There are some general conventions that many compilers follow, especially when targeting specific operating systems, but there's also room for variation and customization. Compiler behavior can be influenced by factors like the target platform, the compiler version, and user-defined settings. While there isn't a single universal standard for how compilers resolve paths for finding external modules, there are often conventions and guidelines that developers and compiler implementers follow to ensure compatibility and consistency within a given ecosystem or platform. These conventions may also be documented in the compiler's documentation or specifications for a particular programming language.
I guess you understand now why I'm thinking about this. Like, but it's kind of hard to clarify. But it is an algorithm that is running in my mind, I think subconsciously, which is like a lot of the stuff that you learn about is gonna be completely arbitrary. And it's gonna be based on the standards that came before. So, for example, when it comes to computing and all of this other stuff, the path here, for example, is just gonna be a standard. So, like most of the parts of the things that you learn are just arbitrary choices that people before you made. So the structure of knowledge itself is going to be based on the compound effect of these different standards over time, I think. And I think that this is the one key, like fundamental thing of like optimizing systems, is because if you build things from standards that might not be optimal, what happens is that it becomes an obvious part of the way people think because it's embedded in the way that they learned. So it's like, it's one of those things where is because everyone's gonna start taking for granted, and it's gonna become what's obvious because it just becomes fundamental part of the system, which is another paradox because it is what is generating gravitational force because everything is built on top of that. But that doesn't mean that it is fundamentally the optimal approach. So it might be the case that because of the way that things evolved, things become like worse over time because they are compounded in assumptions that didn't make sense. And I think that this is the fundamental problem with the scientific paradigm, which is a paradoxical thing by nature. And that's probably where innovation is always going to come from, which is just questioning the assumptions of the thing, which is directly correlated with standards. Because standards are probably the gravitational force of a network. So by questioning the standards, you're able to extract what is fundamental from what is the projection of the network into what's fundamental. But what is fundamental itself is just going to be like a higher surface of connectivity between other networks that is going to give a higher resolution of whatever is happening. So I think it's always correlated with the structure of the networks. So like you can view standards as gravitational force between different networks, and when you expand the surface of the nodes, it breaks down. Maybe not break down, but like what is gonna be the fundamental between all the things is just a direct correlation between the amount of nodes, if that makes sense. So what you call fundamental is just the gravitational force over a larger field, in which like a larger set than which includes all the subsets. And the standards are the compression of the accuracy, which is implications that get into local maxima or minima. And probably the optimization algorithm is going to be related to understanding of the meta perspective of standards, because it's always going to be like a fundamental thing where can always have a bigger set, and it's also gonna be related to gravity. So the algorithm is probably gonna be one that the based on the extension of the network. So you can view like the flow of information as being the increasing or like increasing surface of the network is the flow of information, and that increases the accuracy, and that fundamentally goes. It fundamentally becomes a vicious cycle because you're just expanding between standards that are not congruent with the structure of the whole because they can't be because they were built on local maxima or local minima, and they are a consequence of the gravitational force of the network. So by nature, it's paradoxical. So it means that at all points there should be a mechanism that questions the assumptions and that recalibrates based on the new surface of information. And the reason why I'm thinking about this is because it's kind of related to like the main fundamental problem that I always have and the thing that I'm trying to solve, I think. Because the question is always going to be how do you define the distinction between what's fundamental and what's not? And I think that's going to be directly correlated with the surface of the network, because that's what defines the gravitational force and the structure of what's true or not, because it's always relative to the gravitational force of the network that creates the assumptions that creates the systems and everything else. I think I'm going to stop here. I'm going to think about this other stuff. But now, hopefully, this works, and I'm going to test to see. I think the first thing I'm going to do is just try to create a simple file and write this information here based on write the information based on the library here, like using these functions, write this stuff to a JSON file and see if I get any output. After I do that, then probably maybe I'll do the rest on stream, try to figure out how to use the library. I'm gonna have to study the library as well, read the documentation, but how to use the library to parse the information in C to JSON. And this is the last step. Then once I build the graph, I'm gonna pass the JSON file to the front end and see if I can visualize. And then from that point, I'm gonna try to optimize the visualization so I can visualize what's happening on the code. Once I'm able to do that, then I'm probably gonna read all the files on the Python interpreter and try to use the stuff that I built to understand how the Python interpreter works. So bootstrap the visualization process. Yeah, so probably not sure when I'm gonna come back, but I'm probably gonna do this part here of parsing the stuff into JSON next. So